my name is David Clifford.
And my name is James Liberty.
And today we're going to be talking about pumps and pump cavitation. We're going to explain exactly what they are and how they operate, and then we're going to dive into pump cavitation and the causes of it. The first of the two main types of pumps are positive displacement pumps. They squeeze a fluid via a piston cylinder, lobe, or other mechanism. This takes a given volume of fluid and compresses it, thus raising the pressure of the fluid. They are not very common and are used in high-pressure, low-flow environments.
The second primary type of pump is the centrifugal pump. You can see here two of them in Brown Hall that are operating the campus chilled water system for this building. Centrifugal pumps operate by accelerating the working fluid to high velocity, thus imparting a very high kinetic energy and slamming it into a small pipe, whereupon much of that energy is converted into a pressure gradient. And now we're going to talk about some common pump terminology. This first thing that we're going to talk about here is head, which is the energy that the fluid has. Usually it's expressed in feet or meters, and it refers to the height of a column of fluid that has an equivalent amount of potential energy. It is convenient to use for pumps because it incorporates both the density and the pressure of the fluid. The operational characteristics of a pump can be plotted graphically using a pump and system curve. The pump curve and the system curve are both functions of the flow rate and the head in the system. A system is the entirety of everything that's connected to the pump, including the piping and the valves and any large equipment that is being used that is using the water. The intersection of the system curve and the pump curve is the operational point for the given system.
In this graph, you can see the black lines are the pump curves. The blue lines are the pump size and horsepower. The green lines are the efficiency point of the pump as it's operating. And the pink lines are the net positive suction head. Net positive suction head is the difference between the actual pressure of a liquid in a pipeline and the liquid's vapor pressure at a given temperature. Cavitation occurs when the actual pressure of a liquid reaches the liquid's vapor pressure in the pipeline. So what is cavitation? Cavitation is the formation of vapor bubbles in regions of low pressure within the flow field of a liquid. The effects cause pitting, cracking, and erosion, and they greatly decrease the performance of the pump.
This is the model pumping system that we have in the bottom of Clement Hall. The pump closest to the camera is a constant speed pump, and the pump farther away is a variable speed pump. The variable speed machine allows you to control the exact flow rate through the pump at any given point. Using this model pumping system with the clear piping that you can see there in the back, we were able to close off one of the valves and cause the variable speed pump to cavitate at different velocities. Christopher Brennan, in his textbook, The Hydrodynamics of Pumps, presents a thermodynamic model for the causes of cavitation.
In the thermodynamic model of cavitation, the total pressure in the system is crucial to cavitation development. The total pressure consists of the static pressure and the dynamic pressure. The static pressure is denoted by P sub s, the dynamic pressure is denoted by 1/2 rho v squared, and the total pressure is denoted by P naught. Rho is the density of the fluid, and v is the velocity of the fluid. This is a form of Bernoulli's equation. Cp is the pressure coefficient. This is a non-dimensionalized form of Bernoulli's equation above. For cavitation to occur, P becomes Pmin, which is the vaporization pressure. At the vaporization pressure, Cp becomes Cmin, and cavitation can occur. Rearranging and letting Cmin equal sigma, we get the last equation. Sigma is the cavitation inception number, and all flows have a cavitation inception number.
However, this is an elementary model of pump cavitation. In real-life scenarios, there are several other factors that need to be considered. Here on the screen before you, you can see a simplified diagram of a pumping system. The impeller is on the right and it represents the pump blade, and water is flowing from left to right across the screen. The first factor that needs to be considered are particulates in the fluid stream. The particulates can act as nuclei, which function as stress concentrators for cavitation. This means that it may occur before the pressure model would predict, which is analogous to a notched plate in mechanical engineering. The second factor is residence time. That is to say, the time that the fluid is in the low pressure region behind the impeller blade is important because it dictates the maximum size that the bubbles can grow to. Finally, turbulence is also important because the flow in a pumping system is inherently non-laminar and contains many vortices. These vortices also act as stress concentrators like the particulates. Pump cavitation is very detrimental to equipment. You can see from these pictures the results of pump cavitation over a prolonged period of time.
In summary, pump cavitation is primarily caused by the pressure of the liquid falling below its vaporization pressure. However, particles in the stream, residence time, and turbulence all change the exact point of cavitation. Thank you for watching our video, and we hope you learned something about pump cavitation.